as I said, my contribution is this forum is to share our specific experience in terms of latent storage, thermal energy storage with PCM. And as I said, I like to talk about thermal batteries. And as a I-TES, we work since 2017. We are a little bit more than a startup because we have already passed the 5 years as a startup requirement. And we work on thermal battery. We start from zero, not experience, but zero experience on the field, let me say, to develop this kind of device. Now we have growth in a very important way, and so we foreseen very important goals to reach, and we develop internally specific competence because there are something on the book, but direct experience is a different thing. So it's important to receive input from the academic skill and knowledge, also from the paper, but let me say, translate all these aspects to the final application needs something more. And again, in the consortium of the ThumbsUp, we can put our this kind of skill to reach the final goal of the project. I use the same slide that you have already seen in the Adriano presentation, only to help me to go ahead with my speech. The thermal battery is a battery because you can consider, like in the electrical side, is a generator that you can charge and then you can discharge, but with additional features that help to improve the application in the thermal uses. A thermal battery is composed in a very simple way. The final results, it's a tank. Inside the tank, there is an heat exchanger that are immersed in PCM. The PCM, in this slide, we use what as I-TES prefer, because we move with the use of PCM, organic one, bio-based. We don't use an organic one. It's our choice, mainly to have a very low environment impact in terms of also of LACA requirement. There are no issue, no corrosion, no safety and health issue. The performance, the reliability is very high. Now, at the beginning, there are some doubt about this, but at the moment, after these years, 5, 6 years, now we have the confirmation that also the organic one, bio-based, is a good product. In this case, the PCM, we buy the PCM from external supplier, and what we've done in our labs is to test the performance better, because there are a lot of difference from coming from different material, and we test and validate in our lab with our devices. And the heat exchanger is I know that Adriano said before, the heat exchanger is the most challenging aspect during the design of a thermal batteries, because it gives the higher performance compared with other thermal storage, and for sure the water. And then the tank, electrical cabinet is not so important, because usually, considering that the thermal battery is a static device, the electrical cabin is external. Probably, usually it's included in the overall plant where the battery is an auxiliary device. What are the benefits? Now I go very high level, leaving other insight or what you prefer to go deep during the Q&A session. But the benefit that we use we work on with the batteries to give the load balance, typically for the renewable sources, as happened with the more known batteries, the electrical side. Peak shaving is very important. After this slide, I put an example. And also the thermoregulation using the physical characteristic of the melting point where the latent heat works to store the energy. With these three areas that we attack, that we give a higher efficiency of the overall energy use, and also to increase the renewable source. The final goal is to reduce the environmental impact, so the CO2 reduction. The application potentially everywhere thermal energy is used, and we are focused mainly on the industrial application, but also in the residential, also the automotive with the electrical car. There are a lot of implementation also of the PCM or latent heat storage, a smaller one, but there are some experience and so on. And again, you can use directly the heat batteries, for example, recovering waste heat to use it directly as a heat source, as a generator, I said before, but also, and it is more used with an integrated system. Integrated system could be a simply application with a heat pump, but also combined, and we have different experience on that, on this with let me say cogenerator, with the pumps, with the solar thermal sonar, that everything every heat flow goes to the battery, and that the battery become the source for the user. So in this case, you can decouple sources from the user. And in this case, the overall process could be improved very. You can have a very high improvement. So the application is district heating, heat pumps, cogenerator, heat recovery, and so on. If you can go through all the source of technology that we know. I don't put here, but also the hydrogen usage with the fuel cells is a very amazing application that we have studied on the paper, because we are at the beginning, but it's very interesting possibility. So a very small example in order to see with a real graph that we have obtained in our experience. In this case is an application of our battery in a district heating network substation. So an installation on the building, directly on the building in its substation. So we use this kind of storage as a decentralized storage, far away from the central one, where actually there is a very big, large water tank in order to keep the process in control, but also not only from a thermal point of view, but also from the pressure point of view. But in that case, you can have an efficiency, but if you work closer to the user, the efficiency will rise and will grow very in a very impressive way. In this case, what we see on the left graph is the thermal power profile, the power thermal that are requested by the user without the batteries. So you can reach during the morning. In Italy, we switch on the district heating, the user at the 6 a.m. In the morning. So we have a very high request that in this case go until 150 kilowatt. So you have a peak on request. With the batteries, what we have done during the night, where there are very low requests from the field to the central power, we charge the batteries. So the first curve that you've seen from the before the 5 to the half past 5, we charged the battery and then used the charging to reduce the peak. So in this case, the dotted line are not aligned, but I hope that is clear. To cut the peak that we have seen without the battery. In this case, we reach a reduction of the power requirement from the 14 to 16%. And this what means? It means that you can free power that could be used for additional user, so increase the capability or reduce the working the works of the central power. And this example that is considered in a district heating network, you can transpose in all the network, also smaller, like in an hospital, sporting center, and so on. And these are the benefits that you can reach with this kind of application. That is one of the potential application of the thermal batteries. And this kind of results is not reachable with the traditional storage, or you can do it, but with a very high dimension, very big tank that close to the user is not possible to be installed. Then how to design a thermal battery? As I said, there is an auxiliary element that actually the engineer put because they have to put, but without any study, they used to. But in this case, you have to consider it and you have to go deep on the process. You understand what are the thermal profile, the temperature level, and it requires an analysis, an audit, an energy audit before. So at the moment, the requirement to have a product that at the end work and give the results, it needs a big work. In the next year, after this experience become a standard, this could lower let me say the importance of this first analysis. Then a typical battery that we are used to build in order to give and leave some numbers, and are not quite far from the one that we will install in the ThumbsUp project. So there are the weight, I go not number by number, but we can go back during the Q&A. And but there are several several parameters that you can work. The main are the temperature level for sure, and the other one is the power, not in charging, not during the charging phase, but the discharging phase. As you can see, you can charge a battery with a very low power, almost 5 kilowatt. But the same battery, after you have charged it for a long time with the 5 kilowatt, you can discharge in a very close time, but with a very high thermal. So you can boost the power. That is important thing. And these are the most performance that you can, the most important parameter that you can use as increase the performance compared to the water tank, the water storage. Finally, Adriano explained it better, but in this case, only to share what are our approach in our lab as I-TES. We start with design phases, so decide receiving the input, starting from the input receiving by the user, and to the design in terms of size, dimension, quantity of PCM, shaping of the tank, and type again of the heat exchanger, trying to identify the best solution. If it's a new one, we build a very small, that for us, a small means from 3 to 8 to 10 kilowatt hour storage to be tested in our lab. That in the last days we done these activities, and then validate the data that coming from simulation and from our preliminary study. After this validation, we can improve our design, but we are ready to put on the field the final devices, considering that the module, the modularity that are inside of the meaning of the battery meaning is fully it's real. So if it works at 5 kilowatt hour module, it works at 50 kilowatt hour module. So I reached the end, and I hope that I'm clear. That I know that I'm some difficult in English, but and I'm ready for the Q&A or all your curiosity. Thanks.